Okay, in this tutorial we're going to look at how to construct extended Backus-Naur form, which is EBNF syntax diagrams. These are the rules for certain aspects of a programming language. So if we look at our example here, they often work from probably the lower level to more complex. So down the bottom here we have the more complex, which is a character. And the equal sign represents is defined as, and it can be, this means it's predefined if it's in these brackets. So it means somewhere above there'll be some more information outlining what is uppercase and what is lowercase. So a character is an uppercase and there's more information about it, or, that's what this statement means, a lowercase. It can only be one character, there's no repetition. So just for this basic character, it's either, could be a capital A, or it could be a lowercase x, it could be anything within here, but it has to be one or the other. So we're going to focus on constructing this for an integer, and we just need to understand firstly what are some examples of integers. So 3 is an example of an integer. Plus 101 is an example of an integer. Minus 274 is another example of an integer. So we need to create some rules that will represent anything following that type of format. So the first thing I'm going to do is define what a digit is, because I know that an integer is made up of digits. So digit is defined as either a 0 or a 1 or a 2 or a 3 or a 4 or a 5 or a 6 or a 7 or an 8 or a 9, and that's it. I know that it also has a sign. So I'll do sign is defined as a plus or a minus. Now I can start to construct what are the rules for an integer. An integer is defined as, which is that equal sign there, an optional sign. So it doesn't have to have sign, but it can if it needs to. And then I'm going to put in that it is 1 or more digits. And those braces represent repetition, and this shows 1 or more. So if I have a look here with a 3, that is a valid integer because it's not taking the sign. I'll use this here. It's not taking the sign, it's moving on to the digit, and this is 1 or more. So that's a valid integer. If I look at the next one, it's going to take the sign, which is a plus, and then it's going to go to 1, and then the 0, and another 0. And the final one is going to take the minus, and then it's going to go to 2, the 7, the 4, in a loop like that. And that's an example for how an integer can be represented in EBNF. Okay, in this next example, we're going to look at how to construct EBNF for floating point. So once again, we'll look at how floating point can be represented. So 3.1 plus 17.24 and minus 103.374. So there are all examples of valid EBNF for floating point. So once again, the first thing I need to do is to define what is a digit. So as I defined here before, digit is defined as 0, 1, or 2, or 3, or 4, or 5, 6, or 7, or 8, or 9. No need to go further because they're all just repetition of those numbers. The other thing that a digit, a floating point will also have is sign, and sign is defined as plus or minus. Now when I construct what is a floating point, in terms of the rules for all floating points, it's very similar to integer. So it has sign, which is an optional element. It then has the same thing as an integer, which is digit with a repetition of digit. However, it is a fractional number. And what that means is that I have this little decimal point and I've run out of room, I can actually, might just rub it out so that you don't get lost in terms of how much I've done. And so if I continue with this, what will happen is that it's also by a digit with a repetition of digit. Okay, so that line there has just come down to there. So that's an example of a syntactically correct floating point EBNF statement.